From a more practical point of view, why would the SQA randomly whack a resistor in the charging circuit? Well, it's so that you can come back and do V equals IR calculations. Why else would they do it? So here's an example. We've got a capacitor here, we've got a 6-volt battery, and we've got a 100 ohm resistor. So if this was the question, you could start out by finding the current in the charging circuit by saying V equals IR, or I equals V over R. So the current here would be 0.06 amps. You would know at the beginning that the voltage of the uncharged capacitor is 0 volts because it's got no charge Q stored. If there's no separated charge Q stored in anything, then there's no voltage. So the switch is closed, the current will decrease because, well, we've talked about this before, there's an insulator in the capacitor, so the current starts out high but then rapidly decreases, and the voltage of the capacitor builds up to 6 volts because you get to a point where the electrons are pushing back with the same force as the negative side here, and there's no net voltage push. And when the voltage of the capacitor equals the voltage of the battery, which in this case is 6 volts, then you know that the capacitor is fully charged. Now we're going to look at semiconductors. Do you remember the photoelectric effect? What happened in the photoelectric effect? Well, the clue's in the name. Photoelectric effect is when a photon comes into a metal and it jumps an electron out. Now let's zoom into those metal atoms, and remember Bohr's model of the atom said an atom is actually like a block of flats. So what's going on here is, here's an electron in a metal atom, a photon comes in and it gives the electron energy to jump out of the block of flats. So this is the photoelectric effect. So when we are looking in more detail about what is going on in this slab of atoms or slab of materials, actually the energy levels of individual atoms, they tend to merge, and what you get are energy bands. So when you're talking about a material as a whole, so quite a large number of electrons, you will here talk about energy bands of the atoms altogether rather than individual energy levels. And what we'll come to look at is called band theory, and that's where the word comes from. So here's a block of flats with energy bands in rather than energy levels, but it's the same principle, energy going up the way. Here's a block of flats. So we give names to some of the important bands. Now the very top part of these block of flats is called the conduction band. So if an electron is up at the conduction band, then it can very easily move off the top of the block of flats and do something else, like form a current or whatever. So the conduction band is always at the top. Now the valence band is the highest energy band which is occupied by electrons. It's the highest energy band that is occupied by electrons. Now with a metal, the valence band is not rammed full of electrons. The electrons are pretty much ready already to go out the top and conduct heat or electricity. There's lots of space, easy come, easy go. The electrons in the valence band are pretty much at the top anyway, so it takes barely any voltage to make to make a metal conduct, because the electrons are essentially there already. Now with an insulator, the valence band is absolutely rammed full of electrons already. It's like a sports team which is completely full. This is like a sports team which is half empty. If you've got a sports team which is half empty, then people will leave, new people will come in, and actually it's because the sports team's half empty, it's not particular drama. People can come, people can go. Whereas this is like a sports team which is completely full. It's like a successful sports team, and if there's a sports team which is already full and there's no spaces for anybody, then it's very hard for any other electron to come in, and it's very hard for the person in that sports team to announce they're going to go. So in an insulator, the valence band is rammed full of electrons already, so it takes a huge amount of energy to force one of these electrons out. And so it's as if the block of flats has been made taller, because going upwards is energy. So it takes with a insulator, it takes a huge amount of energy to force electrons up to reach the conduction band, Cb, and conduct. And with a lot of insulators, it takes so much energy to do this that the whole material starts to break down if you put enough energy to make it conduct. So if you're wearing a rubber band, if you are wearing rubber gloves and you touch an electric fence, well, that's fine. The rubber gloves will still not be a conductor, they'll still be an insulator. Whereas if you wear a pair of rubber gloves and touch an overhead power line, then those rubber gloves will certainly not protect you. Those rubber gloves will turn into a conductor, but there's so much energy has been required to move these electrons up and conduct that the rubber gloves will in fact melt, so the material is destroyed. Anyway, the important thing is that insulators take a really big amount of energy to move these electrons up to the conduction band and make them conduct. Now there's a third class of material called semiconductors, and semiconductors have a full valence band, so really they're like insulators, but the distance between the valence band and the top of the block of flats, the conduction band, is a hell of a lot smaller than it is with an insulator. Obviously it's quite a bit bigger than a conductor, but it's a hell of a lot smaller than it is with an insulator. And what we can do is we can dope a semiconductor to get it to the point where it's virtually conducting. And why would we want to do that? Well, it's so that a tiny little input of voltage or a tiny little input of incoming photons can make the semiconductor conduct, which means semiconductors are great for switches which take barely any voltage to turn on. So that's actually like transistors, and that's how computers are just full of switches. And computers used to be full of actual metal switches in vacuum tubes. That's why computers were so big. But you can make these transistor switches which are made of semiconductors now incredibly small. It's like nanotechnology, so that's why computers can be made smaller and smaller. Anyway, there's two forms of doping. One form of doping is, here's the block of flats diagram, and you've got the valence band here with which is completely full of electrons. That's fine, but to dope in this sense means you put a bunch of extra electrons on the conduction band, so right at the top of the block of flats. So you sprinkle some extra electrons right at the top of the block of flats. Now these extra electrons stay up in the conduction band because electrons repel. So they kind of hover at the conduction band, they hover right at the top of the block of flats, ready to roll off and conduct. They repel from the valence band underneath, and this is called N-type semiconductors because they're overall negative charge because you've got a bunch of extra electrons. The second type of semiconductor is where you have a bunch of positive holes in the valence band. Positive holes in the valence band. These positive holes must be in the valence band because you can't drill holes where there's nothing to begin with. Up in the conduction band, the conduction band just means the top of the block of flats. Well, at the top of the block of flats, there's nothing there, and you can't drill out holes if there's nothing there. You can sprinkle some electrons on top, and the repelling force from the electrons there just has them kind of hovering at the top, but you can't drill out nothing if there's nothing there. So the positive holes are in the valence band, and they're lower down than the electrons. Anyway, because we've got positive holes, this is called p-type semiconductor, and it's positive overall. Now, it's really if you put a p-type semiconductor next to an n-type semiconductor when interesting things can happen. If the electrons somehow from the n-type can get across the p-type and move down, they're going to lose energy. So electrons from the conduction band of the n-type, if you can get them to the conduction band of the p-type, then they can fall down to the valence band of the p-type where these positive holes are. And if you can arrange it so that this falling of energy is big enough, then this energy jump down will be given out as a photon of light. So think back to the energy level jumping that we've already done. So this is how an LED works. The electrons jump down, the electrons from the conduction band of the n-type somehow get to the conduction band of the p-type, and then they fall down to the positive holes, losing energy and giving out a photon of light. This is how a light-emitting diode works. Light-emitting diodes have to be put in the correct orientation in a circuit. The correct way round is known as forward bias. The incorrect way round is known as a reverse bias. So let's look at reverse bias first. So if we have the negative type semiconductor facing the positive side of the battery, then all these extra electrons rush to the end of the n-type to try and be close to the positiveness, and all the positive holes in the p-type rush to this end of the semiconductor to try and be next to the negative side of the battery. And there's no current, there's nothing moving around the circuit, and if there's no current, then there's nothing which is going to light. Then there's nothing to light up. Well, lighting up isn't going to happen. So the little bar of an LED is negative. The little bar of a battery is negative. So the negative side of the LED has to face the negative side of the battery. If it's this orientation, it isn't going to light. Now, if we put it in the correct orientation, if we put the LED in forward bias, then we have the negative side of the PN junction facing the negative side of the battery. And what happens here is that the battery has voltage push, which goes from the negative terminal around to the positive. This voltage push then moves the extra negative electrons, and it pushes them through the positive holes, and the LED lights up. Now notice, to begin with, even before you attach a battery, some of these negative electrons already drift across into the p-type, and they just sit in those positive holes. If you're not attaching the PN junction to any external voltage, then there's not enough of a push from anything to push these electrons on through the other holes. They just sort of sit there, but that's called the depletion zone. So if you're then going to attach the PN junction to an external voltage source to hope that it lights up, then you have to make sure that the external voltage source is bigger than the voltage push which happens because of the electrons sitting in the positive holes. Because when the electrons sit in the positive holes, that's a little negative area, and then you have a positive area and a negative area which have been separated, and that's a little voltage, isn't it? So as long as the external voltage is greater than the turn-on voltage, which is the voltage as a result of the depletion zone, then the LED lights. And different color LEDs have different turn-on voltages. But you can see here that the negative side of the LED faces the negative side of the battery, and so the LED lights up. So when you explain how an LED works, the SQA give you some very complicated pictures. This type of physics is called solid-state physics. It's actually very, very complicated, and the SQA, in their infinite wisdom, have taken some of the complicated diagrams to do with all of this stuff, which you'll meet at university.